Today we're going to look at an application of eigenvalues and eigenvectors, and we will look at how to find eigenvalues and eigenvectors in MATLAB. All right, so let's begin with this example here. So we have two blocks of mass M1 and M2, and the springs between them have spring constant K. And if we use Newton's second law of motion, we can set up these two equations here. Okay, these two differential equations. And I should also point out that x1 would be the displacement of mass 1, and x2 is the displacement of mass 2. And then next, something that is not immediately obvious here is that the solutions we expect to take on the form y sub I sine of omega t, okay, where y sub I is the amplitude and omega is the angular frequency. Okay. And so what we're going to do is we're actually going to differentiate those x sub i's, and we're going to substitute them into the ODE above. Let's go ahead and go down here and start taking those derivatives. Okay. So if we were to take the, let's say we were talking about just x sub I. Okay. If we were to take the derivative, okay, I'll put parentheses around it. Well, we should get an omega that'll come out front, so we'll have a y sub I omega cosine of omega t, and that would mean that x I double prime would be equal to minus y sub I omega squared sine of omega t. All right, and then next we're going to substitute this into those, again, ODEs up above. And so the first one started off with M1. Let's go ahead and write that in a different color here. We're going to start off with M1. And then we wanted the second derivative of x1 with respect to t. Let's go up and see that that's true. Yeah. M1 times the second derivative of x1 with respect to t. So here's our derivative of x1. It's just I need to make this a y1 here. So if we were to do that, that's going to give us m1 y1. I'm going to put the negative out front here. Omega squared sine of omega t. And then next we'll do minus k x1. So minus k times x1, and so x1 was equal to y1 sine of omega t. Right. And then we'll go back up here. And then we should have plus k and then x2 minus x1. So plus k and then again x2 minus x1. So that would be y2 sine of omega t minus y1 sine of omega t. And are we missing an equal sign here? We definitely are. We should have had one in between the m1 and the second derivative. So I would like to have an equal sign right here. Make sure we leave our negative right there. Okay. All right, so there's our equation. But notice every single term has a sign of omega t in it. So we could rewrite this a little bit cleaner. We could write this as minus m1 y1 omega squared. is equal to minus k y1 plus k y2 and minus k y1. Okay, just distributed this k here and divided each side of the equation by sine of omega t. All right, so next, let's go ahead and maybe combine some like terms. So I noticed that here on the left, we have a y1, and we have a couple more y1s over here. So if we were to add those y1s to each side, so we'd have a 2y1, okay, and I should say 2ky1. Then we could factor out that y1. We'd have minus m omega squared there. And I'm going to also subtract by k y2 on each side. Okay. And we're going to do one more thing. This m here should have been an m1. Okay. But what we're going to do is we're going to actually divide this equation by m1. Okay. Let's go ahead and do that. So if we were to do that, we're going to have this 2k over m1 minus omega squared y1 and minus k over m1 y2 equals 0. So this is one of the equations that we're going to want. But we're going to want to do something similar here. So this was from, ODE number 1. Let's do the same thing with the second ODE. Okay, so this time, I just want us to know every term is going to have a sine of omega t when we go to make our substitution into this equation up here, because x1, x2, and x2 double prime all have a sine of omega t in them. So we're going to start off the same way. We'll take m2 and multiply by the second derivative. Go ahead and write that, m2, and our second derivative, remember, looks like minus y2 omega squared sine of omega t, and we're just not going to write the sine of omega t. So minus, I'm going to write it right here. If I multiply this m2 by minus y1 omega squared, that's taking care of the left-hand side of our ODE. See what we have up above, and then minus k x2 minus x1, so minus k times x2 minus x1, so that's going to be just y2 minus y1, right? This would have been y2 sine of omega t minus y1 sine of omega t, but we've divided that out already. Okay. So there's that. We're getting closer. And our last term here should be minus kx2. So minus ky2. All right, and we'll do the same thing. Let's move everything over. And actually, before we do that, I want to distribute the minus k. That way it's just a little bit easier to see. So we have minus ky2 plus k y1 and minus k y2. All right. And I do see one little typo here. Okay. So this should have been y2. Right. So we were taking the second derivative of x2. All right, now that we have that fixed, though, let's go ahead and add let's add the, actually, before we add ky2 to each side twice, let's subtract by ky1. I just want it to be in this order where I have y1 first. So there's my minus ky1. Okay. And then plus, and now let's go ahead and add over that 2ky2, but I'm going to be factoring that out because I have another term that has a y2 in it. And one more step here, we are going to divide by m2. So minus k over m2 y1 plus 2k over m2 minus omega squared y2 equals 0. Let's go ahead and box this equation here as well. There we go. And let's go ahead and write this in matrix form, and I think something will become a little more evident. So we have our matrix equation here now. Now, if we were to, try to envision an example where maybe we have the same mass, something interesting happens. Okay. Let's maybe do that. Let's say M1 and M2, let's say that these are both equal to 40, and K is equal to 200. What's that going to do to our system here? Well, if we were to plug in K, it would be 200 times 2 in the numerator here. So we'd have 400 over 40. So that'd just be 10. Let's maybe go ahead and write that down. So we'd have 10 minus omega squared, and minus, what, if we had minus 200 over 40, what's that going to give us? It's going to give us a minus 5 here. And we'll also get a minus 5 down here. And over here we'll get this 10 minus omega squared. And what this means is that we can find some useful information here by just finding the eigenvalues of the matrix 10, minus 5, minus 5, 10. Okay. All right. And next, let's kind of remind ourselves of how we can find an eigenvalue. Okay. So is what we'd want to do, okay, and this will make it more clear why we're even saying we're talking about eigenvalues from, you know, this green matrix up here. Well, if we were to find the eigenvalues, we'd want to find the determinant. Actually, let me use a slightly bigger pen here. There we go. Okay. The determinant of this matrix right here. And we'd want to set that equal to 0. Okay. So let's go ahead and do that. Okay. Let's take this determinant. So we'd have a 10 minus lambda squared minus 25 equals 0. And then if we were to actually try and solve for lambda, we could do this in a couple ways. One is that we could add that 25 to each side, and then from there use the square root property. This 10 minus lambda should equal plus or minus the square root of 25, or plus or minus 5, and so we get then that minus lambda is equal to minus 10 plus or minus 5. And if we were to then multiply, let me move this image here a little bit further down. Multiplying by minus 1 gives us lambda equals 10 plus or minus 5. So we get two different eigenvalues. We get 10 plus 5, which is 15, and we get another one, 10 minus 5, which is 5. Let's see how we could have done this in MATLAB, okay? And then we'll see what useful information this actually does give us. Okay. All right, now that we're in MATLAB, I want to bring up, here was our matrix A. Again, we created A minus lambda I. That's what it would look like here. And if I were to take the determinant of this, what I have highlighted here, and distribute, okay, if I were to distribute after finding the determinant, this is the polynomial that we would end up with, or written in a slightly different order here, we have lambda squared minus 20 lambda plus 75. That's your characteristic polynomial. Okay. But is what I want you to see is that normally when you do poly of something, we would be talking about creating a polynomial based on its roots. So you'd input roots into poly, and it would spit out the resulting polynomial. Well, for us, when we actually take a matrix and put it into poly, okay, so rather than a list of roots, if you put in a matrix, it'll actually give you the characteristic polynomial. Let me show you that this is the case. Okay. So you can see here we get 1 minus 20, 75. Okay. And now if we say we didn't want to factor that, or maybe the roots weren't as nice, we could use then our roots function. So I could maybe call this polynomial P, and then from here we could use roots, and this should give us our eigenvectors, which were, what, 5 and 15. See if that's what we get out here. Okay, we get 5 and 15. But there's an even better way we can do this, okay, or an easier way. We could do could use the eig command, EIG. Okay. And we'll see what these outputs are here in a second. Okay. So we have D is our diagonal matrix that actually contains, it contains our eigenvalues, and then our eigenvectors are up here as column vectors. Okay. This would be our first eigenvector. This will be our second eigenvector. All right, so let's switch back to OneNote and see, what information we got from finding these eigenvalues. Now that we're back to our work here for our eigenvalues, let's also recall that lambda there is actually in place of omega squared. So what that's going to mean is that omega is actually going to be equal to, okay, we're going to be talking actually about two different frequencies here. Let me write those. Omega 1 will be the square root of 15. And our other possible frequency here is going to be the square root of 5. Okay. And I shouldn't exactly be calling this frequency. I should be calling this our angular frequency. Okay. So now that we have these omegas, is what you could find is you could find the corresponding period, or you could actually find the actual frequency here, not in radians per second, but in cycles per minute or cycles per second. Okay. All right. Well, we had that omega. Okay. Let's write another equation here. Omega was equal to 2 pi over the period. Okay. All right. And so you may also remember that the frequency is 1 over the period. Okay, so if we're actually looking for the frequency, okay, the cycles per second, okay, is what we could do is we could divide each side here by 2 pi. And so we get W over 2 pi is equal to 1 over the period, which is our frequency. So if we were to use this, this might help us find a couple other things. This might help us find frequency 1. Okay. So the first frequency, okay, should be omega over 2 pi. And I wrote 2p there. There we go. So that'd be the square root of 15 over 2 pi. And again, this would be in cycles per second. Okay. And our second frequency, F2, would be in the square root of 5 over 2 pi cycles per second. Next, let's go ahead and find the eigenvectors and see what they tell us. Okay. So to find the eigenvectors is what we would want to do is we would want to take that a minus lambda I and actually plug in these lambdas. So let's maybe start off with the 15. So for the 15, we'd be looking at what, 10 minus 15, so it's minus 5. Then I have minus 5 here, minus 5 here, and then 10 minus 15 again is minus 5. Okay. And if we were to say add row 1 to, or do minus row 1 and add that to row 2, we would end up with this here, which would suggest that in order, the corresponding eigenvector is going to have the property that minus 5y1 minus 5y2 is equal to 0. Okay? So in other words, y1 is equal to minus y2. Okay. So our eigenvectors that we end up with are going to take the form of having the opposite sign for y1 and y2. It'll look something like this. The only difference between this eigenvector here and the one that we found in MATLAB is the one we found in MATLAB is length 1. Okay. This one here would be length the square root of 2. All right, and one more. If we were to try lambda equals 5, then we have 10 minus 5, so we have a 5 here. And again, another 5 there. And if we were to do row 1 added to row 2, we'd end up with 5 minus 5 in the top, and everything else would be zeros. And so what this would tell us then is that 5y1 minus 5y2 is equal to 0, or in other words, y1 is equal to y2. So our second eigenvector would be 1, 1. Okay. Now, what I want you to note is that the things that are in this vector are y1 and y2. These are the amplitudes, the amplitudes for those sine waves that we were looking at. Okay. And so what's happening here is in one of these, we're describing a case where the amplitudes are opposite. Okay. And over here, we're describing a situation where the amplitudes are the same. Okay. And so the question is, well, what does this look like visually? And here it is. You can see we have these two cases that we're looking at here. One where they have the opposite amplitude, but they have the same frequency. And so in this first case, they're essentially smacking together in the middle and then separating, and smacking together and then separating, and they're going to continue to do that. Okay. In this other one, we also have this really nice motion, but they have the exact same amplitude, so they're going to keep moving right and left together. Okay. And so what you can kind of see here is that your eigenvectors and eigenvalues are telling you something kind of significant about whatever system you're working with.